Okay, let's begin. So I know I said I was done with SSVS, but I want to show you one more implementation. And maybe this is the implementation I should have shown you first. I thought it was easier to understand it without the betas floating around. So I have betas integrated out of everything in the implementation. And that's the base factor I want you to work out for me. So in problem 1 of the last homework. But let me give you some answers to kind of motivate you in terms of what this base factor is for this implementation. So this implementation is a little bit different, where I'm going to carry the betas with me all through every step. So I'm going to sample those betas from the posterior mixture probability of beta j being 0. We have to figure out what that probability is to input it. Or I'm going to sample from the posterior full conditional for beta j, given everything else. And so in this algorithm, I'm using all of the beta j's except for one at every step. That's what this says. Beta minus j is the vector of betas, excluding beta j itself. And so you just have to work this out. Okay, so maybe this helps you to think about it. So I'm just clicking through each variable and I'm updating it. I'm just sampling it from its posterior distribution. So the prior is a mixture. Posterior is also a mixture. And so maybe I know what this thing is and I can write it down and I can sample from it directly. If you didn't know how to sample from it directly, you could still code up an MCMC. What would you do? If I didn't tell you how to sample from something directly and I want to do MCMC, what do? Metropolis Hastings. So you run MH. I could run MH in the get steps if I don't know how to do it, but this one you can work out in closed form because I'm using the conjugate prior again. So my prior on beta j is just pi delta function beta j equal to 0 plus 1 minus pi normal beta j centered at 0 with some variance. Okay, so the posterior will also be a mixture, and it turns out you can work it all out. This is conjugate to the likelihood. So my function is just this, x transpose beta plus error. These are normally distributed, variance sigma squared. So that's how we're doing all of this. I'll say xi. There. So that's going to be normally distributed, and we want to also select while we infer these betas. So this sampler will take longer to run than the one that I showed you previously. So the one that I've been talking about for the last couple days. Somebody tell me why this sampler will take longer to run.
You need to sample for more distributions.
Yeah, it's not just that.
Your betas are floating, so you're not using matrices.
That's right. So remember what I'm doing. So when we figure out this base factor is going to be conditional on the beta minus j's. Effectively, I'm integrating them out by running this thing over t iterations. So I'm doing that integral inside the MCMC. To figure out this base factor, I only have to integrate over one parameter. This is one-dimensional thing that I'm updating, and I'm carrying the p minus 1, other things with me. So this sampler is going to work out that big integration I'm asking you to do. Right, integrate out betas. So it has to converge in beta space, which is entangled with model space in all of this. And so I have to mix over more things. That will take longer. So if I use the GIF sampler to work out my integrals over all these other things right here, it will take longer to mix. So burn-in is longer. More parameters that I'm mixing over, it's going to take probably longer to mix. Saying that, this sampler is trivial to code up if I tell you what p hat is. I tell you what the expectation and the variance are. So what I'm going to do is I'm going to flip a coin with probability p hat, posterior probability of beta j being 0, given everything else. Give sampling. What's everything else? I don't want to integrate those out. I could. That would be nice computationally, but I'm too lazy. And so I'm just going to write down this one-dimensional thing, and I'm going to carry all these with me. I'll show you what that is. If you can do the one-dimensional integral, you can do the p-dimensional one. So I'm going to flip a coin, p hat, and if it lands heads, i.e. the Bernoulli of p hat, so this isn't p hat, this is a 1 or a 0, if it's 1, then beta j is equal to 0. There's no choices. Otherwise, I sample beta j from its posterior distribution in what I've been calling the alternative space, the bigger model. Beta j is not 0. So I have to figure out expectations and variances. So let's just set this up real quickly. How do we find P and V? We knew how to do this in the first week of class. What distribution does betas follow? It's a normal. How do I figure out its expectation and variance? Go, JD. Save me, please.
Just take, so when people taking the empirical mean, and if you know it's normal, you know it's mean.
It's normal. How do I identify the variance in a normal? Quadratic term. So I fish out the quadratic term. How do I get the expectation? I take that variance and I multiply it into the -2 linear term. That's it. So how do I figure out what those things are? I write down my model, likelihood, beta, given x and y. Whatever model I'm using that current x and y, times prior beta j. So that's it. And I look for the quadratic in the -2 linear terms. So what I'm going to do in this part, since this is part of the alternative space, I'm just looking at the part that conforms to the alternative. So this prior right here that I'm going to multiply by is e to the -1/2 beta j over psi squared.
Squared.
Beta j squared. And this thing right here is e to the -1/2. There's a sigma squared floating around in there. Y minus x beta transpose y minus x beta. I probably want to write this out in terms of beta j's and isolate everything else. So let me just write out x is equal to a matrix with this column xj right here. And I have all the other stuff. So this stuff right here is what I might call x minus j. Okay. Similarly, I might write out what the beta looks like. Beta is going to be equal to a vector with one element, beta j, and all the other stuff. This other stuff I would denote as beta minus j. And so I would rewrite this in terms of beta j and beta minus j, in xj and x minus j. So all I have to do is just rewrite this. Y doesn't change. Y is just y minus, and I've got my x minus j and my beta j. So I might write this down using these forms right here and just multiplying through and seeing what happens. So what this thing is, x beta, let's just write it over here. X beta in these equations is going to be x minus j times beta minus j plus xj beta j. That's it. So take those, sub that in, and then look for the quadratic terms. Once you multiply everything out, there's going to be a quadratic contribution over here, no linear contribution in the prior. And so work everything out. And then just identify what the variance looks like. If you do the math correctly, this variance is this. xj transpose xj, 1 over sigma squared, plus 1 over psi squared. That shouldn't surprise you too much. Looks familiar, but I'm just doing things on the beta j. That's why I have the xj transpose xj instead of the whole matrix. The expectation, I can write down as well. Give myself a little bit of room. This is going to be,
Is it
apologies,
psi squared?
inverse.
Oh.
add precisions together, flip the whole thing together.
If we're adding precisions, is it plus psi squared or plus 1 over psi squared?
Plus 1 over psi squared, precision. Adding precisions, inverting. Same calculation as in week 2. It's just a little bit more cumbersome, some of the algebra.
Then it should be sigmas.
Help me, what is it? This is sigma, right? Usually we have x transpose x inverse sigma squared is the variance of something under the flat prior.
It's just because there's 1 over sigma squared and 1 over psi squared,
It's
and they should
because-
be inverse each other, that's why.
It's because I work this thing out, I isolate the beta j quadratic term, and it's being multiplied by that thing. That's why. And it looks like the exact same form you would have gotten in week 2. Expectation looks a little bit different. I'm just giving you the answers. I could not write them down and have you work through them. So what I'd like you to do is just use this framework to try to come up with the other Bayes factor. I want to give you something that if you cannot figure out how to read a research paper, that you'd get from JSTOR or Google Scholar and find these Bayes factors, and you can't do completing the square yet, you can still code this thing out. So I'm going to give you an answer so that you have at least an opportunity to code this up if you don't know how to. Work this out is what I'd encourage you to do. So this is xj transpose xj 1 over sigma squared plus 1 over psi squared times the term that pops up is the -2 linear term. And so this is going to look like this. X minus j transpose y minus x minus j beta minus j. These are residuals. They look like basic regression forms to me. This is the conditional normal form. So if you don't look at that and go, that looks like the conditional updating formula for a normal. If I take a joint normal and I figure out what its conditional looks like, yeah, there's these residual terms that I'm penalizing, that's what it looks like. If you don't know that, go to Wikipedia, look at the normal distribution. Work these things out. So, I'm not saying that I would just intuitively plug that in, but it looks right. I'm just substituting everything in the traditional formulas with the conditioning that I've imposed. Okay, the Bayes factor is the last bit we would have to write down to run this algorithm. So the Bayes factor is always the same thing, manually.
This is the beginning, wasn't it?
Yes. Variance, yeah, thank you. So Bayes factor is always the same thing. Likelihood, beta, given x and y. I know what that's proportional to. It's e to the minus 1/2 quadratic term times that inverse -2 linear times that inverse times that. I would write that down. So e to the minus 1/2 beta j squared. If I've already done this calculation, this is that plus, I'll say minus 2 beta j squared b inverse e. That's what it looks like. That shouldn't surprise you. If that's unfamiliar to you, go back to week 2 of the class. So times its prior on the null space is a very easy integral to do. If I plug that thing in to this, what's this integral work out to be? I'll start writing the denominator while you do that integration in your head. Likelihood beta xy times my alternative prior. So this is just going to be my normal beta j. I'll just write it down. E to the minus 1/2 beta j squared over psi squared. And I'm going to intentionally make a mistake right now. And somebody can bark at me as to where the mistake is. Okay, let's go to the easier question. What's this integral?
1.
1. So that one's 1, the way that we wrote it down. So if I just took it up to proportionality, this thing would be 1 if I plugged in this for the likelihood. And I plug that down right here. So everything's happening in the denominator right here.
By the way, it's d beta, right? It's not d beta.
D beta j, yeah. Where's my mistake?
The D beta J in the denominator, right?
Yeah, it should be d beta minus 2.
Or you reading for different-
This is, the alternative space has this problem. Something obvious, I've given you a check this on all your base factors, and if it doesn't do this thing, you calculated your base factor totally incorrectly. It means nothing. I don't want to see your work. Sierra's got the answer. Feeling cocky. Sierra, help us out.
Normalizing constant.
Normalizing constant. If those are not proper priors that are normalized, forget about it. So, turns out to be this. 1 over root 2 pi psi. So I just need to work out that integral. How do you work out this integral? Week 2.
Complete the square.
Complete the square. It's completing of the square activity. And so if you work it all out, this formula turns out to be this. I'm going to write it down in disguise for you. It's the formula that I always remember for this problem, and I use this sometimes. So verify this. The base factor is a normal PDF where I evaluate it at 0. I have mean 0, and I have my prior variance. Divided by normal, evaluated at 0, given E in V. These are my posterior quantities. This is it.
Is this the base factor or base factor inverse?
It's the base factor inverse. This is the one that you will plug in right here. So this is just a ratio of PDFs. There's no 2 pi's in there. When you complete the square down here, that 2 pi, root 2 pi gets soaked up. So all the root 2 pi's cancel each other. That's it. That is how you code this up. So you have an actual implementation, and it takes a little bit longer to mix through, but it's probably pretty easy to conceptualize. So all I'm doing is sampling from the beta j's, and I have to work out through just Bayes' theorem, what are those? And then compute my base factor. I'd encourage you to do that to verify this formula. What's this number right here? No.
E minus 1 over.
Yeah, normalizing constant. The e to the minus part is 0 minus 0, that's 1. But I've got normalizing constant in there. So this part right here is 1 over root 2 pi psi. All down there. This turns out to be this in the equation. That's how that's appearing. We're always going to factorize out that thing. That slides right through the integrand. That's what the numerator is. I would not put too much stock into this formula, seeing if you can recognize that that's the base factor. Here's how I've done this. I worked through it from scratch, and then I needed a formula that I could remember. I like this one. I can always remember that. So that's it. So week 2 of class gives me E and V. Done that a whole bunch of times. Your notation is just a little bit messier because you have all the xj's and x minus j's. But it's just algebra. At the end of the day, once you do everything and you do this base factor, this is what you get. So let's just conclude and say p hat is just 1 plus 1 minus pi over pi base factor inverse. And this is a closed form solution that I can just write down and plug into everything. So let's go back to the whole algorithm. What do? I flip a Bernoulli with that probability that I can compute in closed form. I check to see if it's 1 or 0, and I update accordingly. SSVS. Lots of implementations of SSVS. So now I'm carrying the betas and conditioning on them. What was my other version of SSVS? I didn't really care about the betas. I just wanted to find models. And so I just searched through model space and integrated out all of the betas. So instead of writing down this one-dimensional integral, I had integration over an entire vector of betas.
So if you do this where you try to learn these betas, will you get the same, I mean, do you expect different answers than if you
Same
select
answer.
the model first and then optimize the parameters?
They're the same. What's the difference? The computational cost.
Okay.
So that's it. That's MCMC 101. I can always do Metropolis Hastings. Just give me a proposal. What would you use for a proposal for this if you couldn't do the math? What's a good proposal?
For beta, just normal, I guess, at 0?
Yeah, it's not going to work, right? Because I need something to induce actual zeros. If I use a proposal that never actually gives me zeros with some probability, so it has zero mass over 0, I'm not going to load that thing up with zeros, so it won't give me the point mass mixture form. So if you try to do that, you will take infinity to converge. So you're right, it does put support on it, but getting those mixture weights right between the zeros and the non-zeros, you're going to take forever to converge, because with probability 0, you're going to be proposing 0. Saying that, it's still possible. How's that probability 0? Probability 0 stuff happens all the time. Just not in your lifetime. It won't happen again. You can ponder that. If you don't understand that, think more about continuous distributions. Philosophy aside, so what's a good proposal? Not normal. JB?
Well, we're talking about do like the 1/2 equals 0 and then 1/2.
Yeah, I could just sample straight from my prior. So I could use my prior as my proposal. I know how to sample from that. So I flip a coin, I take a 0 with some probability, or I sample from a normal with the complementary probability. So that would work. That'll take even longer to converge. So that's what MCMC is all about, is coding these things up so that they can run fast. So easier to conceptualize maybe, run through those calculations. It will behoove you to be able to work this thing out and come up with that answer. It will really, really, really help you to be able to do this and show this. Should I say it again, or did you just hear what I said? Annie,
I heard it.
what did you hear?
Oh, I anticipate that'll come up on the exam.
So covert about these things. I'm gonna have you work that out. So better do it. And motivation for being able to do the p-dimensional thing if you want. If you want to compare these implementations later on, that's what I really think the name of the game is. If you want to learn an MCMC, every time you see a new algorithm that you're kind of interested in, put a couple hours aside and go code it up. So see how it works. Okay, that's it for SSVS. So a new implementation, just sample the betas. And they'll be coming in as zeros or non-zeros. Okay, so I didn't use my model indicators in any of this formulation. I'm going to write it down that way. So maybe that's how we'd start. Please.
So I got pretty confused. Why do we first sample the J and then sample it again?
I don't sample it again. This beta J, how I sample it, this is how you do it in code. So this is math expression. This is algorithm. I didn't tell you how to do it. I just wrote down some math. This is the implementation of that.
All right, so the first line is not part of the algorithm.
Yeah, this is just math notation. I can't plug that into a computer and get anything out of it. I gotta code something up like that. So
Oh, I see. So
these are the same. Equal. Same. Beta J sampling from that is this line of code, these couple lines of code. Okay, cool. So if you did do it twice in a row, what do you think would happen? If I sampled beta J and I just did it again and I did it for every beta J,
We just take twice as long.
just take twice as long.
Be good second one.
I'd get the exact same answer. So it'd converge at the same thing, I'd just take twice as long. I could say, I want to sample beta 1 one time, and I could sample the beta 5s 5 times in succession and update them. It'll still converge. If beta 5 was sticky and hard to sample, that's what you end up doing. So I can sample them as many times as I want on each parameter, so long as I'm consistent throughout the algorithm and how I'm doing that. Detailed balance will hold. Okay, SSDS, I love this stuff. Apologies for trying to bring in the model indicators first. Maybe this would be a better thing to show you guys the first time, but it's the first time I've shown this in my Bayes class. So thanks for bearing with me.
So in the Bayes factors numerator, is that 2 beta j instead of 2 beta j squared? Like the E?
Huh?
It's just a
Oh, yeah,
parentheses,
sorry.
equal zero.
This is the -2 linear term.
Yeah.
Okay, that's just-
That's where that's coming from, quadratic term. So I already can write down my everything because I've done some work already to figure out what those conditions are. Yeah, you're right. Sorry about that. That's the linear term. Here's the quadratic term. Dirichlet processes in a nutshell? Let's do it. So I think you might even have a chance of understanding this. You ever looked at Dirichlet process paper? Any of them? Who has? Look at papers, glance at them, even if it's just for like a minute or two. So the brain will start to absorb that information in 6 months, and then the next time you look at it, it'll be easier to look at. But Dirichlet processes. There's a lot of measure theory that's usually invoked to describe these. I'm going to show you algorithmically just how we use them. Okay? Let me first tell you what the process is. So I'm going to write down some notation. G comes from a Dirichlet process, and a Dirichlet process has 2 inputs. It has a base measure, and it has a diffusion parameter. And I'll tell you how these are used in a second. So I just want to give you some terminology. This is called the base measure. It describes a distribution. I can plug anything for it that I want, some distribution. I'll show you an example in a moment. And this is going to determine the number of, I'll say, a priori determines the number of expected clusters. So Dirichlet processes are a mechanism that are used when you want to cluster something, group something, stratify something, however you guys want to talk about this, when I don't know how many groups there are. So keep in mind things like k-means, I have to input k. When you studied mixture models in my class, you needed to know how many mixture components there are. I gave you some offline procedures for trying to determine how many mixtures there are, so once you have something fit, then maybe I can use a model selection device for determining how many clusters there are. So you can compare BIC ratios. So something like that. I can take k-means output, write down the model, use a Bayes factor or something like that, or AIC or likelihood ratio, whatever your favorite thing is. You'll start to have opinions once you play with them. So, but Dirichlet processes are a mechanism for trying to figure it out in a big MCMC framework. So basically, this is going to act as a prior on groups. This is a prior on groups or clusters. Clusters, components, all the same word to me. Okay, so that's what DPs are. So let me show you an example. Here's a Dirichlet process. I can't write this down. I can't give you a mathematical formula for it. It's a process, something that I get from continually doing something stochastic. So here's what this process looks like. I'm going to write down my base measure. So this is going to be G naught. It's a distribution. Some dist. Okay, maybe you're thinking of this as a normal. But I'm giving you the distribution, not the family of distributions. I've got it parameterized. So for example, maybe this thing is a normal, 5, 2. Why would I pick that? I wouldn't for anything. I don't know. So, but that's just a distribution. So here's a Dirichlet process. I'm going to sample from the distribution. So step one is I sample from it, G0. So this is going to be whatever I'm sampling right here. I'll call this theta 1 if you want. It's a prior. We usually put it on parameters. So my distribution is going to describe things over parameters. So that's theta 1 right here. So this is just a value of theta. So this right here is thetas are getting sampled from a normal 5-2. Then I'm going to make a decision on my next coin flip. I'm either going to sample that again, or I'm going to sample something else. And there's going to be a probability of sampling it again. So step one, sample theta 1 from a normal 5-2. Step two is I'm going to sample theta 1 with probability 1 over 1 plus alpha. Or I'm going to sample again from G0. What probability am I going to sample that with? This happens with alpha over 1 plus alpha. Okay. So what you notice is if I sample theta 1 again, I have a clustering effect. It's grouping things together. So it has the ability to sample point masses with some probability. Okay, so then we continue. Continue. So here's how we do it in general. Is I'm going to sample theta I. So this is going to be some previously sampled point. And I'm going to sample it with probability. I'm going to write down n theta I. This is going to be the number of times I've sampled. Previously. Okay. So for example, if I sample this again on the second step, that would be 2. Okay, so if I have 2 theta 1s, I've sampled it twice. Divided by n plus alpha, where this is my total number of samples. Or, I'm going to do this for all the theta i's, or we'll sample from G0, this distribution, with probability alpha over n plus alpha, my total number of samples. That's a Dirichlet process. So what I'm doing is I'm grouping things together, and my probability of sampling from that group again is proportional to its membership size. So if clusters are big, if they start to form and I've sampled from them, I'm even more likely to sample from it again. That's a Dirichlet process. So I'll show you how to infer from a Dirichlet process in a moment. So Dirichlet processes, that mechanism that I've used right there can be used to cluster things. So the clustering effect is happening when I sample the parameter again. So there's a couple incarnations of this, different ways you can think about this. There's the polyapern process, there's the stick breaking process, at least the truncated one that you can use inferentially, and there's the one that I usually describe called the Chinese restaurant process. And so Chinese restaurant process is derived, that name is derived. If you've ever been to like a true, authentic Chinese restaurant, so you can't find them around here. Okay, but you can find them in big cities, and you can certainly find them in China. So, but I'm talking the real one, you know, and they operate a little bit differently. And so if you show up at lunch and they're booked, they're going to do one of two things. They're booked, all the tables are full. All the clusters are packed. So, I shouldn't say the tables are full, but all the tables have somebody at them already. And so, in an American restaurant, what do they tell you to do? Go away. So, how dare you come here without reservations? Do you have reservations?
Yeah.
So, sorry, our wait is 2 months. We've seen that episode of Seinfeld. So, gotta get to this restaurant. Chinese restaurants are a little bit more forgiving. So, they care about selling you food. So, they're gonna sit you down at a table that's already occupied. And hopefully they're gonna sit you down at a table where you're kind of like the people at the table. So, they're gonna judiciously say, white guy, sit at the table with the other white guys. So I've had that happen. And so, cool, hey, nice to meet you all. You ever gone to one of these restaurants? So, or they're gonna do this other thing. They're gonna say, let's pull out a new table from the back. So push everything to the side, we'll cram it in, and they're gonna open up a new table. So if I don't look like anybody, they're like, this guy doesn't look like anybody at this. He can't sit with them. Those customers are not gonna come back. So we're going to give Scotland his own table. And I sit there all by my sad self until some other weirdo walks in and they go, yes, now you sit there. So that's a Dirichlet process being run inferentially. That's called the Chinese restaurant process, and it's named for that reason. So let me show you how this works. So let's say you have some data. X's. Okay, so this is just a whole bunch of high-dimensional vectors. Maybe they live in some space, and this might be some clustered data. So in 2D, it might look like this. Clustering in 2D is kind of fun, because I'll trust my eye more than I'll trust the algorithm. Mostly, unless it's buried in noise and I just can't see through it. So, but there's 3 clusters right here. Okay, so this is X1, this is X2, it's X3, so on and so forth. So, here's what the Dirichlet process looks like. So this is how you run it in a GIF sampler. So all I've described to you is a probability process. That's the forward probability process. That's how you generate things out of the Dirichlet process. Now I want to use that process as my prior to try to infer parameters. Okay? So right here, there is, and I'm going to put 1 point over here, and I'm going to put 1 point over here. So that's me in a Chinese restaurant, sitting by myself. So these are, a whole bunch of people that look kind of similar, and they're having a good time, good conversation. This table's a little bit smaller, but they've got friends as well.
There's another person who's alone.
Yeah, so this poor sucker right here is even weirder than me. So they put him in the corner. So, okay, so basically I've got these groups. But I don't know it. I don't know what generated them, I don't know what the groups are. So this is how we figure it out. For each group, so the algorithm will initialize it, okay? So all algos are initialized. Now I'd love to initialize it with all of these people are sitting together, or all of these people are sitting together, and all of these people are sitting together. But it's the whole point of the algorithm. It figures it out. In high-D space, you can't look at this. So if I blow this into 5-dimensional space, you're going to have a hard time visualizing what the clusters look like. So for each group, we'll compute f x tilde given x at the group. So I'll write this down, Ci. So this might be component I. Or group I. Or table I. So now we have a new term. Going to the Chinese restaurant metaphor, that's table I. So I'm going to compute this thing right here. This is the posterior predictive distribution. So this is going to be f x tilde given theta and x, all the x's there. So the idea is that there's some true answer. This is going to be fx tilde, and I'll write it down 1 I. This is going to be, let's just call this component 1, component 2, component 3, component 4, and component 5. Okay, so this is just a pictorial, that's the actual truth. So your algo is figuring out what this truth is. So I'm going to work this thing out, and I'm going to integrate over my base measure. So this is going to be g, well, let's just write it down, pi theta, which is going to come from g naught. Okay, so that's my base. This is your prior. That's how you use this in a Bayesian setup. So this is my base measure that I'm just plugging in right there. D theta. Integrate all the parameters. So this is the posterior predictive distribution. And I'm also going to work this out. This is called the predictive distribution. It's not posterior. It doesn't have any data in it. So you'll see this written down a lot. And so this is going to be fx tilde theta, whatever my models are. So whatever I'm modeling in each one of these tables, this could be a regression model, it could be anything you want. So it's got parameters theta that underlie them, and I've got a Dirichlet process on those things. This is my base measure as well, d theta. And so I usually call this the margin, but in DP land I'll call it the predictive distribution. That's just fx tilde. So I'm just integrating through that, whatever that model is. So I'm modeling something at each table. I'm calling that f. And so I'll put an I on here. So here's what the Dirichlet process does. Is we have some sort of seeding. So I have this thing initialized with my boundaries drawn. So let me draw this again. Maybe this is step 1. Here's what the data looks like. Here's my initialization. Cluster, 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 cluster. Horrible initialization. Okay, I put everything in something. I think I used the true number of clusters when I initialized it, but you can use any number you want. So here's the idea. I'm going to go to this data set, and I'm going to select an individual. Let's say I grab him. I'm going to remove him from the data set. And then I'm going to go to my original answer, my whatever my initialization is, the cluster assignments, and I'm going to form these distributions. So this is I to 1 to the number of groups, or tables, or components, or clusters. So I'm going to take that one individual, I'm going to work through all of these things right here, and I'm going to plug that individual into these functions. And if this number is very, very large, then I'm inclined to sample from it. I'm inclined to say that's which table that individual should be sitting at. So the idea is the Chinese restaurant doesn't have clairvoyance on how to put you at the table, so they sit you down, and then every minute or so they say, some individual, go stand up, and go sit at every table, and see which one you fit at. Okay? So that's just here. That measure of fit is written down here. It's going to be conditional in all the members at that table minus you. You are right there. So posterior predictive is just measuring fit, how well you sit at that table. And then I'm going to put some weights on it. So I'm going to even say if you fit there and there's a lot of people, wow, you must really get along with all those people, you should sit there. But if you go and you fit pretty good, but nobody's at the table, then I should downweight that. I want to group you together. So we'll sample membership. So I'll say cluster membership through this mechanism. Multinomial. And I'm going to write down n C1 over n minus 1 plus alpha. F1 x tilde x C1. The minus 1 is because I removed myself from the data set. So I have to normalize by something different. F x tilde, however many clusters I have, number of components, groups, clusters, tables, given x, however many people are sitting here, so C, number of components. I'm going to look at C, number of components, over n minus 1 plus alpha. And there's going to be a final possibility. Instead of just seeing how well I fit at all these things, I'm going to see how well do you fit by yourself. And this is going to be alpha over n minus 1 fx tilde. No data, no membership at the table. So these are group members. Okay, so here's the whole DP algorithm. If I can work through those posterior predictive distributions, all I'm going to do is I'm going to lift somebody up from a table. I'm going to put them into, I'm going to see how well they fit. So I'm going to plug these things into the posterior predictive densities, and I'm going to scale them by their memberships at those groups. And I'm going to do one for a separate table as well. How well do you fit by yourself? That's how much weight I'm going to put on that. So alpha is influencing the probability of the restaurant tier bringing out a new table. So it's a prior, and so in small data sets it has a lot of influence, and in large data sets alpha doesn't matter a lot. So I'm going to do that for every individual, and I'm going to keep sitting them at different tables that I'm going to sample with this multinomial coin flip. So number of components plus 1 coin flip, and then I'm just going to keep doing that for every individual until individuals start to coalesce at the tables where they belong. Ben?
And some of these weights slightly more than 1, since the NCIs add to n.
NCIs add to n minus 1,
N minus 1.
because I removed myself.
Remove it.
That's where the minus 1 comes from. And so I renormalized minus 1. So all the NCIs add up to n minus 1 because I've removed myself from the thing. So it's kind of this cross-validated fit thing that you're doing. This is a well-governed process. Lots of people have described the mathematics behind that, what this is really doing, but this is all you do. You flip these multinomials over and over again.
At the very end of the infinite, are we ending up at one group?
If you do, how do
We
you,
are ending up to one group.
that means it didn't find any clustering structure. So if it can't ever open up a table. So this will open tables. If you all of a sudden have nobody at the table, the restaurateur takes that table and puts it away. So that's it. That's a Dirichlet process. Have fun reading all those measure theoretic papers on this. I will say this, modern day Bayesians are always doing this Gibbs sampling thing. If I couldn't work out the posterior predictive distributions, I would have to vary the thetas into there, and I'd have to mix over the thetas. That's how Bayesians kind of operate, is we find the full conditionals, we work them all out, and we code them up in blocks. And so this is an infinitely modular scheme. I don't like something about my model, vary in a new full conditional in there, change that parameter. So that's it. So I think the hardest part of this class is Bayes is an entire field. It's not just one thing. And this is one avenue down in that field. And so I think I could go on probably for about 5 more years and tell you about Bayes stuff. So there are advanced Bayes classes here. And most of the learning that you'll need to do is probably on your own. So stock your bookshelf. Give me a call if you get stuck on something, and I'd be happy to talk it through. I think that's it for now. Thanks, you guys. It's been a wonderful semester. Thanks for all of your patience also with me going overboard. Jake, you've been especially terrific.